Okay, welcome to chapter 2. We are gonna really start looking at how molecules are connected together here. And this concept is a wee bit abstract, all right? And how molecules interact, you're certainly familiar, hopefully, at this stage in your life, the idea that an atom can be both a particle and a wave, okay? And it can exist with these properties pretty much simultaneously. It's in the sense of a resonance structure, truly is neither a particle nor is it truly a wave. It's really both. But just like in a resonance structure, we can pretty conveniently allow ourselves to uh, pretend it's one or the other just to, put ourselves in an appropriate reference frame. So if you think of a particle as a wave, where you have a nucleus somewhere in the middle, okay? And you could say this is your nucleus. And if that's your nucleus, then there's some sort of wave function that can describe the electron density or the electron wave function, really, on both of these sides. And that wave function is solved by Schrodinger's equation, which we may or may not get into. It's not necessary to really fully understand bonding, but at the end of the day, these are wave functions. And wave functions can have a sign, and the sign, of course, positive or negative, in the context of a wave or a physical property, that's kind of hard to describe, right? So light can have positive and negative uh, components to it. Obviously, your eyeballs cannot distinguish a positive wave from a negative wave, but they exist. And in that sense, it allows waves to come together and interact and even cancel, right? So a positive wave interacting with a negative wave will add together to create no wave, right? So a positive waveform plus a negative waveform will end up with uh, destructive interference, right? And that, you know, we'll get into that in just a second. Now, how to translate this into the orbitals of atoms is basically each orbital, an s orbital, p orbital, these are all mathematical models. These are all models of electron distribution. And we draw them as sort of like these balloon animals, but they have actual uh, phases, and those phases, when they combine, they tend to just do basic arithmetic. And so if you consider what an s orbital is, right? In an s orbital, we draw it as, you've got a nucleus in the center, and then we say an s orbital is a sphere. All right, it's a sphere, and it's somewhere around there. It's got like some shading over here to really show that it's spherical, and the electrons are swimming around here quite happy. They can go anywhere they want. They cannot go into the nucleus, but maybe got a second electron here. It can go wherever it like in this sphere. And this sphere is actually a probability, and it's kind of hard to draw three-dimensionally that the electron is more likely to be nearer the nucleus than it is out here, right? So somewhere out here, sure, an electron can be out here. It's unlikely to. And that's essentially what these images are trying to depict. They also have a graph, like a 2D graph component that you can draw for what a sphere looks like, right? So if I were to draw my nucleus again in the center and say that's my nucleus, right? And then I could draw what my electron probabilities are about that nucleus. They would be asymptotically close to the center, and then they would fall off to the side. Again, asymptotically. So there would be the probability, and this is your distance from the nucleus. We'll just call those d, right? And the probability of finding an electron is related in here. Okay, so the higher it is, the more likely you're going to find the electron. And in an s orbital, it kind of makes sense, right? You would, like I said, an electron will want to be closer to the positively charged nucleus, and so as a consequence, you end up with some distribution that looks like an electron is you're almost certainly going to find it by the nucleus, but every once in a while, it can be out here. You know, it could be out by Saturn, right? It could be, you could have an atom in your hand and its electron could be all the way at Saturn right now. The probability, obviously, is utterly negligible, but mathematically, totally possible, right? And so this is the description of your s orbital. You'll notice, of course, the s orbital, I have simply relegated the whole s orbital as being positive, right? These are positive wave distributions. I can flip this, of course, because there's nothing that says I really can't. And I wonder if I can flip it. If I hit style, what happens then? No, maybe I can't. Maybe I can't rotate it after I've drawn it. Well, maybe that's something for me to learn how to do. But I could flip this so that the blue parts are now upside down, and it's negative, okay? So even your s orbital has a positive and a negative attribute. I've just drawn one, but you can draw a negative version of the same thing, all right? And you'll remember your p orbital, because we drew that a while ago, right? So your p orbital has one of these where it's got a nucleus, right, in the middle. And then they're the lobes. They're sort of the balloon animal things. And they come out here, and then they go out here, and you're most likely to find electron density, of course, closer to the nucleus again. Well, I take that back. I'm sorry. And you're more likely to find electron density actually more like right here, where the orbitals are a bit fatter. And that's your p orbital. All right, and what does that look like graphically? Graphically, you have same idea, nucleus in the center, except for your p orbital now. You have a probability distribution of finding electrons somewhere greater out here. It passes through the center and then it comes out here. Now you notice it doesn't approach anything asymptotically. It actually goes through 0 at this point, okay? At the very center, it goes through 0. And at that point, we call that a node. And at the node, there's 0 probability. So in this depiction, just like in the one above it, there's 0 probability of finding an actual electron in the nucleus. But unlike the s orbital, the p orbital comes with itself its own plus and negative. They have a positive and negative distribution within their orbital. So that makes it fairly easy to wrap your head around in how these things actually form bonds, right? Because as I was saying up here, positive plus a negative causes destructive interference, and of course a negative plus a negative, or a positive plus a positive, creates constructive interference, right? So if I were to take a p orbital, if I were to take two p orbitals, and I can actually now, I definitely know I can copy this. Copy, and then I go paste. If I were to take this one, all right, and rotate that around. Let's not do that. And draw a second one. All right, that's facing it. Well, I drew the negative going upwards. That's weird. I don't know why I did that. Usually you draw the negative going down, but whatever. And there we go. And here's my second p orbital, right? And I guess I'd have to make that negative now too. And that's my node. Now if I bring these two together, those add up. So if I take these two, right, and I'm just going to take this and just like, and that's going to create a bond, right? Because that's going to go, not the little green arrow, but see, I'm going to overlap those two negative things, and then they're going to be suddenly quite large. And you're going to have a nucleus here and a nucleus here, and then you're going to have your little P lobe over here. Then you have a huge P lobe right here, and you're going to have a little guy like there, and that's going to be plus, and that's going to be plus, and that's going to be super negative, right? And it's huge, obviously, because that is your bond. I put it here. We're going to do the opposite, right? What happens if we go and actually bring it together the other way? Okay, what do you get? You have the positive side coming in here and the negative side over here, right? So this is another way these orbitals can interact. You come in here and they're going to subtract from each other, right? So you're going to actually end up with some kind of weird bonding scheme if this were to happen, where you have your nuclei. We're going to just draw the same business up there. Nuclei here, nucleus here, except now all we really have is that positive lobe here. Those two actually disappeared, so there's nothing in between them, and then the negative up here, right? So that is unusual. It's not disallowed. In fact, it happens. And what you've created actually here is an area of no electrons in the middle. And that sort of bonding is actually something we call antibonding. Okay, so up here we call it a pi bond, but let's just call it bonding. All right, so that's a bonding interaction, and that's an antibonding interaction. All right, so these are two ways orbitals can come together to cause constructive or destructive interference. And as a consequence, you get two kinds of interactions, bonding and antibonding interactions. And this is important because, as I discussed in the first part in chapter 1, I had made a point when I was discussing bonding of hydrogen atoms that you take a hydrogen atom and another hydrogen atom, and they both come with two orbitals. And when it makes a molecule, you still have two orbitals. Let me redo it now, having done all this, and see if that makes more sense. All right, so let's go back to our hydrogen example. And our hydrogen example is really fun because it's just a hydrogen atom and a hydrogen atom, and I can draw them as spheres because that's all they are. They're just the s orbital, right? And then they've got an electron, and they got an electron. And so these two could come together, and I drew a plus, and that comes together, and then they get mushed into something that looks like this. And that is H2, right? Hydrogen gas. And I drew down here, I drew a energy landscape. What does this actually look like? I drew something that looks like this, where you've got an energy, and I said you come with two hydrogens, right? And both of those are 1s orbitals, and each one comes with one electron. And a hydrogen atom, remember, they all want to become their noble gas, so they all want to form something with a filled outer shell, and in the case of hydrogen, that's two electrons. So when they come together, you cannot get rid of an orbital. They end up forming the more stable. So what I just drew up here, two electrons spun differently, and then I said they formed up here. And remember, I called this one the sigma bond, and I called this one sigma star. Now, sigma is your bonding orbital, and sigma star is your antibonding orbital. All right? And where do those come from? Well, and this is, I'll show you, this is your bonding interaction here. That's what that looks like. Because an implicit, or I guess what I implicitly said, is that this is the positive waveform of the s orbital, right? That is, if I scroll up here, this. But I said also there exists equal likelihood that those orbitals will be negative. So a second interaction, so if there's a negative, you have two different kinds of interactions. You have two positives come together, and that's constructive, and that creates a hydrogen bond. You could also have two negatives to come together, right? Two negatives, just like as I did up here, I combined two negatives, and it made a bigger negative, right? It's not, that's sort of how that works. So two negatives come together, that forms an bonding orbital. But it doesn't work. What doesn't happen is if the positive and the negative form orbitals, right? So, and we draw this again to sort of help jog your memory or remind you that this is sort of like that's the positive and that's the negative, right? You have, and the negative form has an electron distribution that looks more like asymptotically here. And this is the positive where it comes together here. Right? And if you try to combine these two, they cancel. And what you end up with is your anti-bonding interaction. And that is quite different because now you have an H and an H, and there's no bonding interaction between them. So you still have your outer lobe, and then it sort of takes like, I don't know, this sort of appearance here. Okay? So there's no interaction here, right? That's your antibonding. Your antibonding interaction. So you may wonder, why do you have an antibonding? It doesn't do anything, right? It's like broken. And that's a good point. Why do you have an antibonding orbital if like it's empty all the time and it's unstable? Well, in hydrogen, nothing, honestly. Well, I take that back. In hydrogen gas is not terribly reactive unless you have oxygen around. And how do you suppose oxygen interacts with the hydrogen gas, right? So if you're an O2 molecule, and so if you're an O2 molecule and you want to light hydrogen gas on fire, you've got electrons. There's a lot of interaction. And from an organic chemist perspective, it's going to be the electrons that are going to go in and interact with hydrogen, and they've got to do something. And where do those electrons go? Here, right? So that's not a great place to be sticking electrons. But if your reaction is literally on fire, that's enough energy to be throwing electrons around willy-nilly into really high energy orbitals. And then once it gets in there, it creates water. All right, and water is super stable. It's far more stable than hydrogen gas, especially if you have added like fire. That's supposed to be fire. So that is the point of the antibonding orbitals. The antibonding orbitals are empty orbitals that can receive electrons from other atoms so that they can do chemistry. All right? So in some senses, your antibonding orbitals are where you do the chemistry. So that sort of explains why you have antibonding orbitals, okay? Now, we've talked about atoms coming together, and you're forming a bond right here, right? And we even sort of discussed in a prior lecture bond lengths. And I said that they were, I heavily implied that they were fixed, right? So I said single carbon-carbon bonds are 1.54 angstroms. And that's an unusual number, perhaps, because it's like 3 significant digits. And there's actually a reason for that. So when you're talking about bonding, and we'll stick with our friend hydrogen here for an example, there's a distribution where you have some amount of energy, and really what a bond is trying to get to is some lower energy, right? So as I drew up here, single isolated atoms are higher energy than the bond. So if I were to draw 2 hydrogen atoms, they would be out here, and they've got their electrons, right? And those are essentially, we'll call that the relative zero, where they're fine. You know, hydrogen atoms can equal 0, they're fine, they're going to react because in reality, energy equals 0. They're not terribly happy, right? And then they come closer together. And so as they come closer together, the energy actually starts to go down, okay? And at some point, they get close enough to form a bond. And this is good. This makes them happy. They're able to share electrons, and electrons like to be shared. They can spin, they can flip spins and even stabilize each other. But as the atoms get closer, they actually their nucleuses start to get too close, and that starts to become unstable. So your bond minimum is essentially when you have this nice distance where the nuclei are far enough apart that they are not threatened, I guess, by each other, and the electrons can interact peacefully. Now, you eventually get to a point where the nuclei are just too close together, and that is a higher energy starting material than the separated atoms, all right? So this is energetically where you get bond lengths from. And this sort of depicts graphically why bond lengths have a specific energy. So let's look at p orbitals now, because we just looked at a sigma orbital and sigma bonding. Now, p orbitals, we had already shown a bit briefly that you have your nucleus, and then they have these lobes, and then these lobes can actually, if one is positive, and a shorthand actually for differentiating positive and negative is actually just to color one of the orbitals in. So if I color one of those orbitals in, that will help you see that these two are matching orbitals, right? And if I combine those two orbitals, what I would end up getting is something with a great big orbital in between and two of these little antibonding orbitals. And the middle part, you'd get a bonding orbital. So this bonding orbital that exists in the plane of the nucleus is technically a sigma bond, even though it's created by two p orbitals. And if it were the opposite, as I'd illustrated a bit up there, where the filled in side combined with the unfilled side added here, you would end up with the antibonding orbital, a sigma star orbital. Okay, so that's your antibonding orbital. And we kind of covered that already. Now, of course, pi bonds, bona fide pi bonds, kind of exist outside of the plane of carbon, right? So in the case of a real pi bond, you'd have your carbon here, and instead of your, just to be clear, you know, they have 3 of these, right? And so these are your px orbitals that are combining. Now, in a real pi bond, of course, you have other orbitals, and there's also the py and pz orbital. And we will talk a bit, we'll just use the py orbital as an example of bonding that's not in the plane, right? So you can have 2 carbon atoms with their pi orbitals, and these can have a phase overlap, all right? And what this does is it actually combines together, right? So this overlap just simply becomes quite extended. So it's now the whole area up here. Oh, that made it oval. That's actually unhelpful right now. I don't really want it to be an oval. This whole area up here is now the pi, 1 pi orbital. And then the orbital down here is the open pi orbital, right? So the positives added together and the negatives added together to create the pi orbital. Likewise, you can get the antibonding orbital from this by combining them in a different way, right? So instead of combining them where the phases are matched, you combine them in a way that makes the phases unmatched. And if you try to combine those, which you can combine them, right? It's just math. They're not inherently uncombinable, but they do end up sort of making these bit silly looking antibonding orbitals that sort of show repulsion. You notice the orbitals in the p systems and increasingly in the other, they actually change when they form molecules because they're a bit more complicated than the s orbitals. They sort of change shape a bit. But this is normal. Like, you don't actually have to have the lobes touching, but if they can interact through space and through bonding space, that leads to a stable interaction. And this, of course, the bonding interaction was going to be where you're going to put your 2 electrons, and then the antibonding interaction is where potentially electrons from a nucleophile are going to go. And it's harder to put electrons up here because that's an unstable spot, right? You really got to pump an electron up to get it in here. Likewise, it's kind of hard to pull an electron out of here. But when this becomes a nucleophile, if you want to use these pi systems as a Lewis base and donate those electrons are going to come out of here, okay? So that starts basically a concept as we move from CHEM's atomic theory to OCHEM now, molecular orbitals. All right, and molecular orbitals in organic chemistry are different, right? Because we kind of realized a long time ago that carbon is a 3-dimensional structure. Looks something like this. You've got carbon here, all right, and then you got a substituent here, and you got a substituent here. Well, you know, that could be another carbon. And then actually you've got like a substituent coming out at you, right? And then something going off in the back away from you. So carbon is like a 3-dimensional structure. It's kind of hard to draw this. Let's say it has this carbon, and then you have this looking here, and then you have something coming out towards you. That's that's like a tetrabromo methane, right? And then carbon actually has something pointing away from you. What does that look like in 3 dimensions? Thankfully, the internet provides a good little GIF of this thing rotating, or GIF, I don't know. But you can see, if we open this up, how this hydrogen comes in and out. So this is methane. But when it comes out towards you, it's got this wedge shape. And when it's away from you, it's got this dash shape. And all of this this from here to here, actually, that's a defined angle, and everything that goes between here and here, that's actually the same angle. All right. So all of these angles are actually 109 degrees. 109.5 degrees, if you want to be quite specific. And that geometry is fixed. It's like superset. All right. And so you've got to think, you got to remember back to your orbitals, right? You got the big red ball. Okay, so that doesn't have any angles in it. Anything can go wherever it wants. That's your s orbital. And then carbon, of course, has p electrons, so it's got these orbitals that go. They're 90 degrees to each other. All right. So how do you make 109.5 degrees from these two orbitals, right? Because those are your options. Carbon is 1s, 2s, 1s2, 2s2, 2p2. And those are your two combinations. So how do you mush them together in order to make these angles? And that is a trick. That is a trick that kind of baffled early physicists, because these orbitals make a lot of sense. But the angles that they form do not match up with the angles made in nature. So the idea came out. Carbon does not actually have and does not actually react with this sort of structure, all right? In fact, if we consider the atomic structure of carbon at all, and I'll draw it here, down here, right? We just consider the atomic structure of carbon at all, right? It's 1s, 2s, and then we got p, 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 2p, and then it's got 6 electrons. We follow all our rules. What this basically shows is that 2 of the electrons, as I've drawn here, right? So 2 of these electrons that I've drawn, remember the y-axis here is actually in increasing or decreasing energy. These would be more energetic than these two. We've said carbon has 4 valence electrons, and at no point did I ever say that 2 of them were less energetic than the others. So again, that seems really odd to try to say, all right, so carbon is not made out of a bunch of 90-degree angles. It's made out of 109.5-degree angles. And carbon has 4 equivalent or degenerate electrons in the valence shell, not 2 high energy and 2 low energy electrons. So when you consider it, actually, none of that makes sense. Your classic orbital theory doesn't really make sense. But if you combine, all right, if you merge all this stuff together into what's called hybridized orbitals, if you hybridize, does it make sense then? All right. And yes, as a matter of fact, of course it does make sense. So what would combining an s and a p orbital look like, right? So an s and a p orbital, if you mix them together, so you'd start off with your s orbital. And your p orbital, that's shading, by the way, to show you it's a sphere. And your p orbital, and that's to show you that one has a positive and one has a negative interaction. And you put your nucleus in the middle, and you combine them. You end up with something. What does that look like? So you got like your s orbital here, and then you got your p orbital. Whoop, wrong tool. Your p orbital here, and then you put them on top of each other, right? And okay, so you got an open, we'll say, for the sake of argument, that's a positively charged lobe, and then this is the positively charged lobe of the p orbital. So you combine your 2 p orbitals together, and this is sort of gamish. And what does that gamish look like when it comes out on the other side? it starts to look like, all right, well, I guess we should come up with a color. I don't know what that color is. A purple, maybe? What you end up with is combining these positives. These positive and this positive comes together. You end up with this really big orbital on one side of the nucleus, a node in the middle, and then the negative side of this is not totally negated by the positive of or the negative doesn't totally negate the positive of the s orbital. The p orbital volume is, I guess you want to say, smaller. So you end up actually with that pretty tiny little orbital here, right? And this combination, this weirdly shaped thing right here, we call an sp orbital, okay? So it is a combination of the two orbitals put together. And when you combine two sp orbitals together, okay, so you have the start of the big node, the big node, I'm sorry, the big orbital and the big orbital of your atom here, or your nucleus right there, and you got the little puny side. So, you know, it's like when you skip leg day, you're big on one top and then little tiny sticks on the other side. You end up with bonding through here, okay? So bonding goes through here, and that looks like beautiful sigma bonding to me. Now, this is combining the s and px, yes, px orbital. All right, I didn't combine the py or the pz orbital, even though they still exist. So they're still part of these carbons, these putative carbons. So I can still draw in these orbitals, and you have to, because you have not accounted for them, right? So there's still a py orbital up here and down here, and there's still a pz orbital coming out here. All right, and the other one's behind a big purpley sp1. All right, big p orbital here, big p orbital here, pz orbital coming out here, right? And if these are the same phases, then guess what? You get a pi bond here, and you get a pi bond here. So what have you actually made? So if you want to draw the Lewis dot structure, there's 2 electrons in this orbital, 2 electrons in that orbital, and 2 electrons in here. All right? And then there's nothing connected out here, right? This is like, you've got 2, 4, 6. So each of these carbons right now does not yet have a full octet. 2, 4, 6. And then it's missing something, and if we balance that with a hydrogen, we've actually made the molecule acetylene, right? So this is, if we were to just draw these in, acetylene. And if now, what does that over here look like? We've got our carbon, so we'll just call that carbon, our carbon. You've got your central sigma bond, your sp bond. Then you've got 2 pi bonds. And then I haven't drawn them in, but you would have a hydrogen that could interface with this little knobby guy out here. And that would be your triply bonded molecule, okay? And what's great about this, right? What's really important about this is that it totally explains. Acetylene in real life is 180 degrees. This is 180 degree bonding, right? It's a totally linear bond. And so this sp hybridization accounts for all of those interactions, and it makes it 180 degrees. Now, when you think of something that is at the other end, the other extreme, when all the p's combine with all the s's in our traditional carbon, that's an sp3, right? So if you were to take your s bond and then your 3 p orbitals. I'm not sure where that was going. Let's do the px. And then the pz. So that's your py, px, pz. Let's give them some phases. And then give them some nuclei. All right, now how are you going to combine these? So we know by looking at that spinny little GIF up here, 109.5. So when you combine all these things together, you end up with something that looks like this. Carbon in the middle, and then your hybrid orbitals, where you have one hybrid orbital coming out here, one hybrid orbital coming out here. And then if you pretend like these are actual volumes, they have volumes. They're bigger than p orbitals because now they've got s orbitals in them too. So they can't distribute them 190 degrees. You kind of have to distribute them 109. Like the best way to fit them is 109.5 degrees out. So this orbital is going to have to come out at you, and this orbital's kind of got to go away. And if you start populating these with hydrogens, and that one's like coming out at you, and this one's like tucked away, and then you end up with this geometry that if you start rotating around here, it starts to look like that, right? So it gives it three-dimensionality. So only with this way can you get that three-dimensionality. And what's cool is I have made 4. I started with an S. 1, 2, 3, 4. I started with 4 orbitals, and I've made 1, 2, 3, 4 sp3 orbitals, right? And all 4 of those sp3 orbitals are now the same. So buried deep in here is a utterly unhybridized 1s orbital, okay? That hasn't hybridized at all. It's in the very, very core. But all of the 2 s and p orbitals are now hybridized together. Gas and Smithian. Gotta draw them like this. There we go. Now all of these are equal. 1, 2, 3, 4. And now I can populate them just like that. So I took, if you'll remember from up here, this wonkiness, this unhybridized system where I had 2 electrons are not degenerate, and through hybridization, I've made them degenerate. So that's the sp3. And y'all are smart. You could probably figure out sp2 and how combining sp2 actually produces the 120 degree angle. And I won't go through it here, but because I like drawing them, I'll just show you that the Sp2 system creates the hybrid orbitals that have one Sp2, all right? So if combining 3, these are 120 degrees apart, by the way, right here. And I left one out. There's only 3. Where's the 4th one? Why, the 4th one is going to be the, say, the PY. Sure, why not? That can be the PY. And so if I were to combine 2 sp2 orbitals with something that looks like that, another 120 degrees out here, draw in my nucleus. And this one also has a p orbital and a py configuration. I would have 1 bond and a pi bond and 2 empty orbitals, which, I don't know, you can fill them with whatever you want if you want to make your own molecule. Well, I'll put hydrogens in them. So now carbon, if you count your number of electrons, 2 electrons, 2 electrons, 2 electrons, 2 electrons, 2, 4, 6, 8. Both of these carbons, whoops, have 2 electrons. Both of them have now a full octet. What's that look like when we draw that out? In pretty organic chemistry, carbon sigma bond, pi bond, carbon. Let's do our hydrogens. They're going to be 120 degrees apart. Hydrogen, 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 and that is the molecule ethene. Okay? And if you imagine going up here and doing some sort of connecting to 3 instead of what I've made here, I've made methane, but you put 2 of these together, you make ethane. So ethane, ethene, and ethine are all explained, the geometries, and ethene, believe it or not, does indeed have a 120-degree angle. All right? And these 2 bonds, and that's 120 degrees from here too, are all explained, including the energetics of bonding. And here's a quick question, right? These sigma bonds, right here, the sigma bonds, they're all basically the Sp2 hybridized ones. They're all lower in energy. Is the pi bond higher in energy, right? Would we draw something like this? Your inner carbon, and then your S2sp2, which has 3 bonds, 1, 2, 3, and then you still have that 2p orbital. Yes. So as it turns out, the p bond, the pi bond up here in ethene, and just like ethine, totally different chemistry, all right? When you do the combination and fill in these orbitals, the pi bond becomes more reactive than the sp2, the sigma bonds. All explained through hybridization.